Hi everybody. We are going to treat ensembles. Today, specifically, we are going to talk about micro-canonical ensemble. And our starting point is something that we developed on Sunday, is our average quantities. Okay, so for example, for energy is a sum over all the state over the system, the probability to be of the system to be this state nu multiplied by the value of the energy at state nu. But we can generalize this and say, well, if we have a different observable, we don't have energy, we have magnetization, we have temperature, we have resistivity, we have whatever you like. So a given observable O, the average value of the observable that we can observe in an experimental lab or calculate somehow is simply the sum over all different states of the system, the probability of the system to be at this state multiplied by the corresponding value of this observable at this state nu. Great. Now, statistical mechanics starts over here because over there, and the question is, how do we know what kind of states do we have? How do we know what are the different probabilities to be at each specific state? And what are the observables for those different states? Microcanonical ensemble, it's the simplest possible assumption that you can make. So when we start to learn probability 101 in our first undergrad studies, we start with something that we call uniform probability. Probability. So what is a uniform probability? If we have our state space, omega, uniform probability means that any given observable or any given result of the experiment in our state space is equally probable, meaning that the only thing that we care about are how many results of an experiment that we have, and all the probabilities to getting this result or that result or any other result are exactly the same. Okay? So this is uniform probability. The microcanonical ensemble is based on this assumption that all the different states in our system have exactly the same energy. The energy of all the different states is the same. Okay. And they are all equally probable. So basically, if you look on this expression over here, so for a given energy, we are counting all the different states that we have. All of them have exactly the same energy, okay? And those values over here are also all the same because, well, I can have two different states. They all have the same energy, and the probability to be in state A or to be in state B exactly the same. So this is the simplest assumption that we can make about any experiment, probabilistic experiment, is to assume that the probabilities are uniform and we need somehow to connect it to the energy. So we assume that the system is defined by the value of the energy. There are many states for a given energy, fine, but all the states are equally probable. All right, so it seems easy. what it actually means and how I can connect this assumption or description of microcanonical ensemble to something real. So what do I mean real? So for me, or at least for us for now, thermodynamical laws. Okay. So I need somehow to connect this statistical assumption and microscopical behavior, and I need to connect it somehow to whatever I know about thermodynamics. I have the first law, I have the description by energy, I have the description by free energy, Gibbs, enthalpy, whatever you like. And I need this somehow, this equal probability of all the different states, to connect it to thermodynamical laws. And at least for microcanonical ensemble, I use entropy. So remember, so far, the only thing that we ever said about entropy is that entropy is a monotonically growing function of energy, and we have derived, seen, observed the principle of maximal energy in equilibrium. And now we need to perform an additional step and say how entropy is connected to all the different states, those states, of the system. So it's not exactly clear, it's a little bit like a leap of faith forward. We are claiming the following thing. So we again going to use our principle of maximal entropy. What this maximal principle means, so let's assume that we have a system. And inside the system, we have a barrier. Okay. Inside the system, we have a barrier. Now, the principle of and this barrier, the position of this barrier can vary. It can go from left to right. Okay. And we do not constrain the position of this barrier. Let's assume that we have a gas inside. Now, the principle of maximal entropy says the following thing. Since the position, let's say this x, is unconstrained, in equilibrium, the position of the barrier is such as to maximize the total energy of the system. Okay. So, there is a specific position, general position, and it will be obtained, or how I find it, I'm basically saying I have a maximal energy, I have a maximal entropy for this specific position. Okay? So this is the equilibrium state. I also know that if I will try and constrain the position of this barrier to any other position, okay, so I have a very specific position that maximizes entropy. This means that if I will try to constrain the position of this barrier a little bit to the right, a little bit to the left, or a lot to the left, a lot to the right, the entropy is going to go down. So this means, this maximal entropy means that the moment that I introduce constraints into my system, entropy goes down. Okay. So the system has to be unconstrained in some equilibrium, and addition of any new constraints is going to give a reduction of the entropy. This is the maximal entropy principle. Great. Now, if we think about a system and it has many states, and then I introduce a constraint into the system, what will happen to the states? So any constraint, so this is the principle of maximum entropy, and we can say introduction of constraints reduces the entropy. But we also know that introduction of constraints reduces the number of states. of the system. Right? So if basically I'm saying, well, no, this state is not allowed, it's a constraint, definitely the number of states are going to be lower. If I'm saying this state is achievable only if some other state is achievable, it also reduces the number of states of the system. So I can say, well, there is something similar in those two. So the entropy goes down and the number of states also goes down. So what can I assume, or this is the leap of faith forward, I can say maybe entropy equals to number of states. Can I make the following assumption? Is anything wrong with this assumption? What do you think? Yeah.
The left-hand side is extensive, but
on the right-hand side?
If you increase the size of the system, it's going to grow exponentially.
Okay. So entropy is an extensive quantity. What do I mean? I have two systems and I add them up, and the number or the entropy is just going to double itself. That's it. So entropy is extensive. Entropy is extensive. Grows linearly with the system size. But what about the number of states? So let's assume I have a system with two states. Okay, 2 bit. I have a system and it's a 1 bit. It's either 1 or it's either 0. Okay, so I have 2 states over here. I add another system that also have 2 states. Okay, so it's either 1 or either 0. In total, how many states I have? 4, right? So here I have 4 states. But let's add to those 2 bits another system with 2 bits. Okay. How many states I have for this combined system?
60.
Okay, so it is 2 to the 2 to the 4. But here I have 4 states. Here I have 4 states. So together it's 8, right? So it's not growing linearly. If I just add the states over here and add the states over here, it's in total it's going to be 4. 4 plus 4 is 8, and it's definitely smaller than 2 to the 4. So the number of states, we're looking on bits, for example, but it works for any other states, the number of states grows exponentially. Entropy grows linearly. Okay, so how we will solve this puzzle? We basically say, if I have a quantity that grows exponentially, I'll take a log out of this quantity, and it grows, and then it grows linearly. So I would say, so S equals to log, so it's a log on basis of E, of omega, and omega is the number of states of the system. But here I need to introduce a quantity. For the quantity, because I need the units to be right. Okay? So the units are Joule to Kelvin. This is K Boltzmann. And K Boltzmann is 1.38 multiplied by 10 to the minus 23 Joule per Kelvin. So it's a constant that basically makes all the units right, because number of states is unitless, log of the number of states is unitless, but the entropy have a specific unit, which is Joule divided by Kelvin, and I just introduce here this K Boltzmann. Why exactly this number? It's connected to some other properties, thermodynamical properties. As a good theoretician, in a lot of cases, I can basically say, well, let's change the units and say K Boltzmann equals 1, right? What are the preferred units of a theoretician? K Boltzmann equals 1, the speed of light equals 1, h bar equals 1, everything that you can imagine equals 1. But we're not going so far away from experiment. So we need to introduce something that's related to the MKS system, and this system, K Boltzmann, is this number. Okay. Yes?
The Boltzmann constant includes the change of the basis of the logarithm.
If you're going to take here, like for example, log over 2, it's going to modify your Boltzmann constant somehow. Yeah.
But most of the cases we are working with log 2.
It depends on how you define everything. So basically, you will have a different Boltzmann constant. Great. So we will see an entropy definition due to Shannon, which is something that's related to information theory. It doesn't care about this K Boltzmann over here. So when you're only talking about the number of states and you do not care about anything else, so usually in information theory they will use log on the basis of 2. Here we're in physics, so we need some sort of a units, and those units are affected also by, or this number is affected what kind of logarithm you're taking, which is what is the basis of your logarithm. All right, this is good. Why it's good? Because remember we are in microcanonical ensemble. So assumptions: all the states are exactly equally probable. The energy for all those states is exactly the same energy. Okay? So the energy is not modified. And now, the moment that we have entropy, we can somehow relate this to thermodynamical equations that we already know and familiar with. How do we know it? So we use that 1 over T equals to ds to d. So the way to operate with this microcanonical ensemble is the following. You have a system. In those systems, you know that everything is equally probable if you have, for a specific given energy, all the different states of the systems are equally probable. The way to derive some equations, meaningful equations, you need to compute the number of states for your energy. Okay. The moment that you compute the number of states that you have for your energy, you take a log, multiply it by K Boltzmann, and you have an entropy. And in order to derive some thermodynamical descriptions, equation of state, and etc., you just simply use the definition of entropy, of temperature with respect to entropy and energy. And that's it. Very, very, very simple. It applies only but you've seen this in the thermodynamics class, but it applies only to simple systems. Why? Because the moment that the system becomes complex and it have many states and it have constraints, there is a mathematical, technical difficulty to compute this omega e. So we use this ensemble only just to, well, this is how you start defining ensembles, statistical ensembles, and in order to get forward to more complex and much more interesting ensembles like the canonical ensemble and the grand canonical ensemble. Okay, let's use one single example where we actually using microcanonical ensemble. Any questions? Two-state system. So we have in our system n particles. Number of particles equals n. The particles are non-interacting. Each particle have exactly two states. So this is the energy per particle. So the energy of each particle is either 0 or epsilon. So that's it. So this is all what we have in our system. We have n particles. They are not talking to each other. Each of them can occupy either the lowest possible energy, which is, we can define it as 0 always, or the excited state, which is epsilon. Okay. Our question is, compute the specific heat of the system. So basically, C equals d E d T. All right. So how do we do it? Remember, the prescription for microcanonical ensemble is always very easy. Compute the number of states, write the entropy, take a derivative of the entropy with respect to the energy of the system. That's how you obtain temperature. And then from this equation, you can compute whatever you like. For example, you can compute the specific heat of the system. Okay, okay, so what do we have? So we have n particles. And we ask ourselves, so the energy of the system is E. E is the energy of the system. Now you can say, and we have many states, all of which correspond to the same energy E. The question is, omega is the number of states. Okay, so we are back to probability 101, and we ask ourselves, in how many ways, right? So each of the particles can be either at 0 or at epsilon. So if our energy is E, how many particles are excited in the excited state? E divided by epsilon. So E divided by epsilon, the number of particles in the excited state. Now, I don't know which particles are in the excited state and what are the particles which are not in the excited state. So basically, I can ask the following thing. E divided by epsilon is the number of boxes that I have inside my system. I have n particles. So the total number of states inside the system is by how many ways I can pick up out from n particles and fill out those e to the divided by epsilon boxes. So it's basically choosing problem, combinatorial problem of choosing e divided by epsilon out of n. So omega is what? And choose. Whatever. So it's a binomial coefficient, right? You want me to prove it to you? It's you build the whole tree. It will take something like 45 minutes to prove it, but if you want to choose out of n a specific number, all right, without correspondence to the order of which is who and when you picked it, this is the result. So this is n factorial divided by e by epsilon factorial and n minus e divided by epsilon factorial. Okay. Basically had to choose e over epsilon out of n. Great, very simple. Now why it's simple? Because I choose a two-state system and they are not interacting. If they were interacting, it was much more complex. Okay, so this is the first step. The next step is to say, great, I have an entropy which is k Boltzmann log of omega, which is k Boltzmann log of n factorial divided by e by epsilon factorial and n minus e divided by epsilon factorial. That's it. Very nice. How do I continue? Sterling, great. Right? So what Sterling tells us? N factorial, the Sterling approximation is square root of 2 pi n divided by e to the power of n. So this is Sterling approximation. You probably have seen it as log of n factorial equals to n log n minus n. Right? Now, there is an additional part that people usually forget. So this is a square root of 2 pi n. So we can add as, and it's small because it's a logarithmic correction. So we have plus a half a log of 2 pi n. But nobody really cares about this because this is of order of n, this is of order of n log n, and this is of order of log n, so you don't really care about it. Now, what students are told the first year that it works for which n? Large. This is not true. This works for n greater than 1. Okay, so you can plot this, you can compare the n factorial to this function. Okay, and it works extremely well also for very small numbers. Okay? It's already not so true when you throw away this logarithmic correction, but it's still fine. You don't need n to be 10 to the 23. That's the point. Sorry?
It's from the gamma definition?
Yeah. So basically, you take this and use this gamma definition in integral representation of factorial. Works great. So you don't need n to be extremely large. N can be 10, 20, and it's already extremely good approximation. Okay, so what we are going to do is to take this guy and develop it a little bit by using the Sterling approximation. So this is Sterling approximation. Okay. Now, we're not going to use this correction. It is there, so you should know. And if you really want to compare Sterling to the factorial, you should use this. But if your n is large enough and 10 is 20, it's already pretty large, you don't really need this. Okay, so what do? We start opening all the parentheses with it. So S equals to k Boltzmann, let's keep it outside. We have log of n factorial. We have minus log of e divided by epsilon factorial minus log of n minus e divided by epsilon factorial. And we close our parentheses. It goes as k Boltzmann, so it's a little bit technical, but those are the calculations with microcanonical ensemble. There always are. There are two difficulties. The first is to compute omega. It was actually not that difficult for this case. The other one is to use Sterling approximation for all the factorials. And with microcanonical ensemble, you always get some factorials because it's a choosing problem. Okay, so we have k Boltzmann. What we have over here? So we have n log n minus n minus e divided by epsilon log of e divided by epsilon plus e divided by epsilon minus n minus e divided by epsilon. Here we have log of n minus e divided by epsilon. And we also have plus n minus e divided by epsilon, and I close my parentheses. Great. So we clearly see that there are some stuff that we can get rid of. And what is this stuff? So we have minus n plus n. This goes away. We have minus e divided by epsilon, and we have plus e divided by epsilon. Okay. And that's basically it. Okay. So let's continue a little bit with this, our dance with the equation. So we have n log n, and I want also to take the n over here. And here I have log of n minus epsilon. So I have n of log of n minus log of n minus e divided by epsilon. And I have another guy. So I have here plus e divided by epsilon. And inside I have log of n minus e divided by epsilon minus log of e divided by epsilon. Okay, so I basically have taken those parentheses, I opened them up, and then I took n as a common divisor. Okay, we can follow this a little bit further, and we can say this equals to k Boltzmann, and here we have n log of what? Of 1 divided by 1 minus e divided by n epsilon. Right? And here we have plus e divided by epsilon log of what? Of 1 minus e divided by epsilon and epsilon divided by e divided by n epsilon. Okay. Looks right. Okay, very nice. Why it's very nice? Because I can invert this stuff, or I can subtract over here, and then I'm having k Boltzmann, and I have here is e divided by epsilon minus n. Let's do it a little bit slower. So I want to combine this 1 minus e divided by n epsilon and this 1 minus e divided by n epsilon. Okay. Yeah. Seems okay. So we have k Boltzmann. And here I have n and I have epsilon. So I have e epsilon minus n. All of this multiplied by log of 1 minus e divided by n epsilon. Okay. So what I have taken, I have modified this logarithm of 1 over something to minus a logarithm. This is why I have minus n over here. And I kept this logarithm as it is, and I still have something that I forgot to sum up, which is minus e divided by epsilon log of e divided by n epsilon. Okay. Now, let's take n out of this equation. So it equals to n k Boltzmann. And inside I have e divided by n epsilon minus 1 log of 1 minus e divided by n epsilon and I have minus E divided by N epsilon log of E divided by N epsilon. So we basically have E divided by N epsilon as some sort of a variable, and we don't care about it, it's outside, K Boltzmann, it's outside, and here we have some mess with those logarithms. So this is our S. Okay. The next step is to say 1 over T equals to of ds over d. Nothing really happens over here, so we can say it is ds to d E divided by N epsilon multiplied by d E N epsilon divided by d. So it is ds to d E N epsilon multiplied by 1 over N epsilon. So what we need to compute is this guy. Okay, so this is why I have written S as a function of E divided by N epsilon. Okay, because the derivative is actually very simple. Okay, so I write here S of x as N K Boltzmann x minus 1 log of 1 minus x log of x. And I need to compute ds to dx, right? Which is, we have N K Boltzmann. Let's look on this guy. So we have x minus 1 derivative, which is 1, right? 1 multiplied by log of 1 minus x. Okay, another guy, we have x plus x minus 1, multiply the derivative of 1 minus x, which is 1 over 1 minus x, multiplied by minus 1. Okay, so, yeah, great. So this is the derivative of this guy. The derivative of that guy is minus log of x, okay, minus x multiplied by 1 over x. Okay. Close our parentheses over here. Okay, so what happens over here? So x minus 1 divided by 1 minus x, and I have minus 1 and minus 1. So this is plus 1. This is minus 1. So those terms got cancelled out. So what we have is that ds to dx equals to N K Boltzmann. And we have log of 1 minus x divided by x. And in general, we have 1 over t equals 2. We take 1 over N epsilon over here. And ds to dx is what? Is N K Boltzmann. Okay, multiplied by log of our x is what? E divided by N epsilon. 1 minus E divided by N epsilon divided by E over N epsilon. Okay, so this is already very, very, very nice. Why it's nice? Because this equation I can solve in terms of E. What was my goal? My goal was to connect it somehow to thermodynamic equations. So there was a lot of math, right? So this is a starting point, and there was a lot of cancellations and derivatives and etc., etc., etc. But eventually we got somewhere. Where we were headed, we wanted to obtain an equation of state. What is equation of state? E equals to something which depends on pressure, volume, temperature. Look on this guy. Okay? So there is E, there is N, which is some sort of a volume of the system, the size of the system. Epsilon is an intrinsic constant, okay? And we have temperature. So all the ingredients are inside. Okay, so let's make this equation a little bit prettier. Okay, so first of all, we get rid of N and N, and we are getting that epsilon divided by k Boltzmann T, very important quantity, k Boltzmann T, equals to log of 1 minus e over n epsilon divided by e over n epsilon. Okay, let's take a logarithm of both sides, exponential. So we have e to the power of epsilon divided by k Boltzmann T equals to 1 minus e divided by n epsilon divided by e divided by n epsilon. So we have e divided by n epsilon multiplied by epsilon over k Boltzmann T. We have e, we have n over n epsilon equals to 1 minus e over n epsilon. All right, so we have e over n epsilon multiplied by e to the epsilon k Boltzmann T plus 1 equals to 1. And eventually we are having that e equals to n epsilon multiplied by 1 over 1 plus e k Boltzmann T. This is the equation of state of two-state system where we have n particles and it's described by microcanonical ensemble. Let's rewrite this formula as E equals to n epsilon multiplied by e to the power of minus epsilon by k Boltzmann T divided by 1 plus e to the minus epsilon by k Boltzmann. It's the same. So first of all, we look on this and we say, well, it's actually have the same the right units, right? So E is the unit, have the unit of energy because it's the energy of the excited state. N is just a number, unitless, the number of particles that we have inside. And here, what we have here, it's also a unitless number, which is fine. Now, can you guess what is this guy? From probability.
Probably to be in the state of epsilon.
Exactly. Okay. So think about it. What do I have? I have n particles. Let's look on one single particle. What is the energy of average energy of a single particle? Okay, so particle 1. E of particle 1. Energy, average energy of particle 1. It can have 0 energy with probability to be at side 0 plus epsilon with probability to be at the excited states, so the probability to be at epsilon. Okay. This is the average energy of one single particle. Now we have n particles. They don't care about each other, so the average energy of all the particles we can n interpret. We don't really know if it's average energy, not average energy, but our interpretation is of what? Is as if we had a two-level system or n two-level systems. For each of those two-level systems, we can compute the average energy, which is epsilon multiplied the probability to be the excited states, and multiplied by the total number of two-level systems that we have in our hand. So this guy is the probability to be in the excited state. Which is very nice. We started with some uniform description, etc., etc., and it gave us a microscopical quantity, a microscopical computation of what is the probability of D in the excited states, and it's related to the energy of the excited state, and it's related to the temperature. So it's already a very nice description. Now, our purpose was to compute the specific heat. CV equals to dE to dt. Right, so additional computations. Now, I will spare you those because we can take the derivative, and it's going to be n epsilon squared divided by k boson t multiplied by e to the power of epsilon divided by 2k boson t plus e to the minus e to the k boson t to the power of minus 2. Okay. It's already an easy derivative of this guy. Now, why it's actually interesting? This is already a macroscopical quantity that we can measure in a lab. Okay, so why we have done all of this? Yeah, you have a theory, you have a model, but eventually you want to make some sort of a prediction. You want to say, I have an identifier, okay, theoretical identifier for my fellow experimentalist. I want him to see something or look on this quantity, which he can measure, or he or she, they measure in the lab. And based on the observation of the behavior of this quantity, I can say something about what happens microscopically inside, right? Because I don't know whatever is going on inside this piece of metal. I can measure the specific heat. I can measure. I heat it up, and the energy rises in some way. I can measure this specific heat behavior as a function of temperature, for example. And if it looks like whatever I got over here, I know that this is a two-level system. I don't need to use my microscope in order to see whatever the microscopic dynamics inside. I need only thermodynamical description. So if we plot this as a function of temperature, this CV, it looks like this. Schottky anomaly. You know this already. Sometimes also called Schottky hump. And basically, why is this happening? So, if you see in an experimental system and you see the Schottky behavior of the specific heat, you know, oh, I have a two-level system inside, or a bunch of loosely connected two-level systems. Why we had this? So think about it. We had many two-level systems. Some of them occupied, some of them excited, some of them are not. Okay. As I raise my temperature, more and more systems are going to be excited. Okay. In general, in total, I have n systems. All right. I have n systems. So so this is the growth of the specific heat. Why? I heat the system up, more particles are excited, the energy grows, so this is why I have an increase of the specific heat. I have more and more excitation in the system. At some point, I continue to heat up, but there are less and less less and less unoccupied levels. This means that I will create another increase in my temperature, and the system energy won't rise up. It basically is going to be stuck. This is why the specific heat, which is a derivative, okay, it's going down. But you can say, Stas, but there is no such thing as two-level system in reality, so we usually have other states over here. Right? So usually we have a spectrum. How can you have a two-state behavior when in the real system, okay, this kind of Schottky hump, if in the real system there are many states above, it's never a two-level system. Well, I can tell you that it's, yeah, in reality we have many states, but what happens if there is this delta, so the difference between the excited state and the next excited state is actually big. So what will happen that if we do not increase the temperature too much, we are going to excite only up to the first excited state. Okay? We are not able to excite further because we haven't invested enough energy. We haven't heated the system too much. Okay? The specific heat will go down. And what will happen if we will continue to heat it up, we will get another rise. Okay? So you can basically learn about the structure of the material, the structure of energetic bands inside the system by heating the system up or cooling it. And the behavior of the specific heat describes to you what is the actual structure that's going on inside. Now, this was a very simplistic model, and we will continue to something much less simplistic, which is a canonical ensemble on Sunday. Thank you.